Hi. And start until I introduce you. Ready to go?
Ready.
Time has come. I've been doing T-minus whatever for a while. So I've prepared some remarks. We're delighted to have Sara Seager speaking today. And I should just sit down because she needs no introduction. But I've prepared these remarks. I'm going to read them because in the interest of time. First, it's great to have everybody here and online. We want to especially welcome Ivan Semenya from the Globe and Mail. Nice to see an old friend back. Sara's a native of Toronto, a U of T math and physics grad, and she did her PhD at Harvard under the supervision of Dimitar Saslav. But Dimitar Saslav was a U of T PhD on computing stellar atmospheres. So a great Toronto connection, and we're always happy to see Sara home to talk about her latest research. She has an honorary degree from the U of T and is an officer of the Order of Canada. Sara's a risk taker with a good eye to which risks to take. This has led to many firsts. For example, models of hot Jupiters, and for today's talk, the diagnostic power of spectra taken during exoplanet transits and the technique of atmospheric retrieval, and many, many more results that you can read about in the citations for the MacArthur Prize and the Kepler Prize, for instance. She wrote about risk in a short biography that I read on the Kavli website and can recommend to you. There she said, "Fortunately, at the IAS, our legendary astrophysics leader, John Bacall, had a visionary and bold philosophy. He believed that as long as the underlying physics is sound and well developed, and the phenomena conceivably detectable within one's lifetime, an astrophysics topic is worth pursuing." And I, Sara, am grateful for this extraordinarily enabling attitude. So, Sara personally drove the development of the new field of exoplanets, and MIT wisely soon appointed her to lead this burgeoning field across that university and internationally. More risk-taking and more insight have followed. Regarding the potential for discovery of life elsewhere in the universe, she developed what is called the Seager equation. It focuses on biosignature gases, today's topic, broadening the scope of potential discovery from intelligent life to any form of life that interacts with its atmosphere. She is working on everything from the biochemistry of what could be out there to novel ways to detect it, like the enabling starshade concept and missions to Venus. Well, now it's time to hear from Sara, and there will be an opportunity for your questions afterward.
Hi, everyone. Well, I've been preparing this talk for a while, and let's see, it may not be what you expected, but I wanted to share with you where it kind of all started. I came across this paper about, I want to say 20 years ago, and this paper is from 1969. Has anyone seen this paper? It is somehow kind of legendary in its initial, like almost like a weird humbleness, hidden, like I don't think people appreciated it until I came across it and other people came across it. What happened is Salpeter, who some of you may know because he's been working in GR, as giant computer codes at Cornell, had this paper, the mass radius relationship for cold spheres of low mass. And it's a very sort of theoretical paper, but we use this to understand planetary interiors today. And here I'm showing you 3 equations that they used in their paper: the mass of a spherical shell, the hydrostatic equilibrium, where a planet is holding itself up against gravity, essentially by Coulomb forces, and then the equation of state, how density, temperature, and pressure relate to each other. They call this cold, so they ignored temperature. And they had come up with a revised equation of state when, at high pressures, when electrons are pressure ionized. So what this means is that, like, think of a really high pressure when stuff's squeezed together so much that an electron pops off. And now nuclei can squeeze closer together, and they get compressed on the inside. And they also rightly said, although you have an astronomy where we like to approximate and kind of hand wave, they just said most of the planet's mass is at high pressure. But trust me, it's not high enough that electrons are going to pop off. But nonetheless, they applied their equation of state, Thomas Fermi-Dirac equation of state, when you have at least one electron has popped off, and the sea of electrons swimming around nuclei, it's all quantum mechanics. But they apparently in another paper had improved it, and they made a way to, it's like many pages of a kind of parameterized fit that could then be applied to models for the first time. So here you can see J and S are Jupiter and Saturn. These units are a bit weird. He has at the bottom log M over M sun. But what you're seeing here are essentially Uranus, Neptune, Saturn, Jupiter, and this is like size of object. And planets would be on the left side of this diagram, where a planet of a uniform, hypothetical mass, think of a small planet, it's a certain size and mass, and if you imagine this one growing, like getting more massive, it should increase as r cubed, right? And it does, but eventually it doesn't anymore until in fact it starts shrinking, and that's because of their equation of state. So this is really interesting. I always loved this one. And I was trying to understand interiors of planets back in the 2000s. And so I read their paper with as much detail as I could and implemented my own set of equations. And I didn't realize, but a couple of years before I got interested in this, our very own Professor Diana Valencia was working on it. And I'm not sure how many people still know that she was on her own as a grad student, really started this field of exoplanet interiors. And she had one professor in geophysics and one also Dimitar. It sounds very like almost incestuous here, because Diana was like my academic sister, I guess. And she brought these fields and started working on it. So what we do in this field is we're taking these equations. You could all do this if you wanted and make a simple model. In Diana's case, she did something more complex. She had 2 more equations for the transport of energy and conservation of energy, so she could include temperature. But when I started out, I also ignored temperature following that legendary paper. But we also didn't just use the Thomas Fermi-Dirac theory, but computer simulations and lab experiments get you the first kind of few hundred GPA. So this is a more modern version of theirs, where I'm now going to walk you through in years as an intro to my talk with just a bit of history. But what I'm showing you here is radius and Earth radii, so it's on a log scale, mass and Earth masses. So this is covering a huge ground, going from 1, 10, 100, 1,000 Earth masses, 1, 10, more. So Earth and Venus are here, around 1 Earth mass, 1 Earth radius, Uranus and Neptune, Saturn and Jupiter. And these curves are just like the ones you saw, it's just scaled differently, and we're not showing you the whole turnover. But these are curves of constant composition, so it's very hypothetical. But if you're imagining a pure iron planet, again, it would grow as r cubed, and this is what Diana found initially in her original first explorations. It stops growing as r cubed eventually, because the inside's getting a little bit compressed, even before those electrons are popped off. And it actually plateaus in a way, so it doesn't sound sort of crazy that you can have an object 10 or 100 times more massive than another one, and be the same size. It just seems kind of weird, although you all know about white dwarfs, which are tiny. So back in 1999, we just had our first transiting planet ever, HD 209458b. And people really did think this field would dead end. They literally thought we just wouldn't have very many transits. We'd just kind of be left with these weird hot Jupiters. You know, we had a couple more eventually. Yeah, then a bunch more. And people were starting to warm up to the idea that we might get a lot more planets. But still, our selection effects are for big planets close to the star. Short, hot period planets, short periods by Kepler's third law, they're close to the star, high probability to transit. We just kind of started filling this in from ground-based surveys. But as you all know where this is going, eventually Kepler launched, we got more and more planets. It's just incredible, isn't it? To have so many transiting planets. And this is still really just a small fraction of all the planets out there because they don't all transit. We still have major biases. There's high temperature, so most of these are at the high temperatures, but we're trying to figure out what's going on. Now we come to 2024, and this is not fully updated, but these circles are planet atmospheres that have had attempted observations. Some of them have resulted in real spectra, others are flat lines or didn't work out. But I just wanted you to appreciate how many planets we have and the huge variety of them. I like to say anything is possible for exoplanets within the laws of physics and chemistry. Because it's shocking really that nature made such a huge diverse range of planets. And I mean, you can see some things from this figure. It's not complete, so you can't read too much into it. We haven't statistically made this exhaustively perfect. But you can see there's no massive, like ginormous 100 Earth mass rocky worlds. They just don't seem to exist in nature. I harbor hope that maybe they're out there around A-stars. We just haven't found them yet, but they're not there. We don't have planets in this corner of the diagram because they would just be too puffy. They just would not be able to hold themselves together under their own gravity. But we seem to have planets everywhere else here. Maybe there seems to be missing ones in here. But ultimately, our goal is to, well, this talk's goal is to tell you where we are at in the search for signs of life beyond Earth. But given this huge diversity, we always want to make we really want to find signs of life, okay? But the small rocky planets are just so small, it's not clear if it's going to pan out. And I'll come back to that later in my talk. So we start by asking ourselves, where else in this diagram does a planet live where it might have life? Or where we should look and not be so terracentric that we can't just go beyond our narrow-minded thoughts. Now, the giant planets like hot Jupiters or Jupiter itself, too hot for life. They have large convective cells that would draw life away from the cooler layers down into the inside where life would just get fried. So we rule those out. But we come down here to these planets we call mini Neptunes or sub-Neptune sized planets. And on this diagram, this is quite an old diagram from 10 years ago, but the point here still holds. This is now planet radius and orbital period. And it really was to highlight the ginormous yield from Kepler. But when you look at this plot, just kind of look at it briefly, I hope you can all see where the most dense part of this diagram is. Again, it's not complete by any means, but I was trying to illustrate for you how common these Neptune-sized planets, sub-Neptunes are. Planets between 2 to 3 times the size of Earth. They appear to be the most common planet in our galaxy. It could be that small planets are more common, but we can't find them all yet. But in any event, these are very common. And you know what? They were found to be common way before Kepler. The microlensing surveys found a couple of these sub-Neptune mass planets way back. And because they're so sensitive, they knew if they found these low mass planets, they had to be extremely common. So we have evidence they're extremely common. We have none in our solar system. And you know what's so exciting about them? Is some people speculate they may be water worlds. Their average densities could be such that they're made of 50% or more water by mass. And we have a thing in astrobiology, follow the water. All life on Earth needs water. If you heard my talk yesterday, that was about Venus and how we might not need water. That's a different talk. But we, for example, we say we want water. So these could be water worlds, so they will be our first place to search for life. And I'm now going to give you a little bit of detail about that, but here is a water phase diagram. You've all seen one version of it. You live this here in Toronto, right? Because there comes a time when winter arrives and those puddles freeze. So you live here, and we have temperature. So let's go back to where we are. I guess we're kind of near the liquid water ice kind of 1 bar. I guess we're around here somewhere. But we have this huge space to play with. And I'm going to assume you've all seen this, or you know what this is, because we have temperature increasing here, and we have pressure decreasing. So you're supposed to see this surface of the planet is at the top, and we're going down onto the inside. This is going to be a bit overwhelming. We can make models. That was the conversation from coffee. You can make any model you want, pretty much. But what these are, they're different planets with temperatures and pressures. So if you make a model of a planet with the 3 equations I showed you and a couple of additional equations for conservation of energy and energy transport, your model will pop out a temperature pressure profile. So what you can see here is some of these temperature pressure profiles, they're crossing through liquid water at their outside. And we can make models, and a bunch of people in the community do this, of these so-called mini Neptune, sub-Neptune sized planets. If we assume some are 50% or more water by mass, they can have water. They can pass through this. Some are so hot, they're just passing through vapor. But look at this, supercritical water. Has anyone heard about that? It's kind of really obscure. On our planet Earth, it only exists, it's nothing we can experience. We don't make it. But at the deep sea hydrothermal vents, some of them are just the right temperature and pressure. There's like the teensiest bit of like legit. But some of these, remember, anything can happen in the laws of physics and chemistry. There have to be sub-Neptune sized planets out there that have this weird supercritical water. We don't understand it. I'm trying to get my colleagues to do experiments to see how like methane and ammonia, how they dissolve or don't dissolve, or how they flow through supercritical water, but yeah. But I was just trying to tell you that in our universe of our computer models, we can always, I don't think we can always come up with anything, but we can come up with, there have to be, they've got to be there, depending on their interior temperature. We don't know the range of what that can be, but we're confident there's some with liquid water out there. So that was my introduction. And I'm now going to talk a bit about these water worlds as our first kind of set of candidates, which are kind of right to search for life in that they have puffy atmospheres, we can search for them. And to talk about atmospheres, we're going to first just talk about the James Webb Space Telescope. How many people here work on atmospheres of exoplanets? One or two, yeah. Well, for those who don't, just give me a moment while I review this. You may already know it, but it never hurts to hear it again. And so I'm just showing you this gorgeous transit light curve. And you've all seen transit light curves, presumably, just unless there's an undergrad who came in from another topic, but transit light curve. And the concept behind transit searches is that the planet can look a tiny bit bigger where the atmosphere is strongly absorbing. So if you look at the cartoon here, we don't spatially resolve any stars like that other than our sun. Also, do you see how the artist made this so perfectly homogeneous? That's going to be important later in the talk. But you also see the artist made limb darkening. I'm just jogging your memory for later. That's nice too. So they did some things right. It's a perfect world in this artist's conception with a very exaggerated planet. But you're supposed to see here that the transit light curve, it's the area ratio of the planet area to the star area. But with an atmosphere, the planet's going to look a tiny bit bigger. So the goal is to look at different wavelengths and see if the planet looks a tiny bit bigger. Okay, are you all with me on that? Because we actually get to see it. Have any of you seen this before? So let's look at this, and if you saw my talk, you saw this, I showed it yesterday, but this is like one of my favorite plots like ever in astronomy. You're seeing relative flux, so the star is normalized to 1, and the time for mid-transit in days, so the transit lasts a few hours. You have a very characteristic transit shape. The black is the best fit to the data from the James Webb Space Telescope for planet WASP 39b. We're looking at different wavelengths in the near infrared, and that's the W in the corner there, going through the different microns. And you're trying to look at the points and see if at any wavelength, does the planet look a tiny bit bigger? Is the transit dropping beneath this best fit, this average best fit? So in my talk yesterday, were like biologists and linguists, so I'm confident everyone can see it. But if you do see it, just like raise your hand or indicate, yeah. It's cool, huh? Do you see what wavelengths it's at? You can shout it out if you can coordinate. 4 point something, 4.3, yeah. Well, wow, this is amazing. By eye, you have all seen an exoplanet atmosphere. And that's how great the data is. It's just astonishing. I bet a lot of you, if you were attending talks when you're undergrad, or for all of us here who've been in astronomy for a while, I bet you've seen some exoplanet atmosphere talks and you were just like, no, it's just nothing. But for legit now, we have amazing data. And that's the whole reason why people are striving for hoping we can find signs of life in an atmosphere far away by way of gases that don't belong. Because we have the Webb, we have the new capability, our first capability ever, arguably. This is a hot, giant planet. It's too hot for life. It's not going to have life on it. And here now is what we really do. By the way, we're taking each of these light curves, and limb darkening matters, actually. We have to go from this to like, we want to know what our spectrum is. So for every wavelength, we need a transit depth. And the limb darkening ends up mattering for the depth and fitting the transit. So now each color, each wavelength is going to be a data point with an error bar. And we're now showing you all the wavelengths together from 3 to 5.5 and amount of light blocked. So the transit itself is blocking out about 2.1%. And this tiny part of the atmosphere is blocking out about let's say we go from 2.1 to 2.3, just to make it easy for us, so it's 0.2%, so it's 2 parts per thousand. See if I got that right. I'm looking for everyone to check that. That's actually amazing, like that's a huge signal for us. So I don't know what fields you're working in, but do you need to go to that to 3 decimal places? Like, I don't know if everyone does, maybe you do, but for us that's a huge signal. The atmosphere for a small planet is like another 2 or 3 decimal places. Question? Yeah.
Can I ask a question about the previous plot?
Sure.
So why is like the like longer wave and like the red lights, the statistical fluctuation seems to be way larger than the blue lights?
It's way larger, yeah.
Is there a reason for that?
It's just, as far as I know, it's just the detector doesn't behave as well at the longer wavelengths. But I'm glad you did notice that, because it comes relevant a bit later in the talk. Yeah, I'm not 100% sure on that, I just want to be honest, but I do think it has to do with the detector.
Thank you.
Sure. Okay, so here's WASP 39b. I just wanted you to see it's got a lot of features. It's a bit hard to see, and this is like the NASA kind of colorful version. But let's just take it from 0.5 out to 5 microns. You're seeing sodium, which is in gas form at these temperatures. It's not locked in a molecule, or it's not ionized like it is in stars. You've got some water vapor, carbon dioxide, and you have this huge feature of carbon dioxide. That's what we were looking at. And if you read the last slide, it said carbon dioxide is not the dominant form of carbon. It's just a very strong absorber. Just like here on Earth, we're worried about parts per million of carbon dioxide. Another thing happened. So the most that exoplanet atmosphere science, I'm just sort of trying this out on you of how you think of this, that people got excited about was this little bump here. Can you see this, this little bump? This was actually not expected. And this is sulfur dioxide. Because in a hydrogen-dominated atmosphere, you're expecting everything to be in its hydrogenated form. So carbon should be methane, sulfur should be H2S. This SO2 ends up meaning there's photochemistry here. And this would be something like in the equivalent of your field, you know, if a new observation comes up and then people scurry to write papers. This was like the paper to write. And so what I've started to witness is that exoplanet atmospheres, it's becoming astrochemistry. And so if you wanted to work on atmospheric chemistry, you go to entire talks and you think you're, it's sort of its own branch of atmospheric chemistry because it's not as detailed as our atmosphere, but it's super detailed. So I'm just putting that out there to you because some talks would now just launch into like the rest of the talk being chemistry. So atmospheres are really complicated, and I do feel compelled to tell you a bit about how we're handling this. This is just a cartoon of an atmosphere showing you like volcano and life, like making, you know, putting out gases. And in this picture, they're just interacting, mixing, but they're getting photochemically altered. And there can be atmospheric escape of lighter gases going to space. And we do have some ways of doing it. I guess I'll skip that equation, but I just am going to give you an overview as to where we're at because it becomes extremely important in our current search for signs of life and our methodology. So we do understand atmospheres, we think. We have some equations. I just wrote them out because I know that you could, I wanted to make sure everyone can get a little bit of a glimpse into how we handle atmospheres. But you can imagine it like 5 equations and 5 unknowns. Conservation of energy, that's always a good one. No atmosphere is created or destroyed in the atmosphere. We have energy transport, so that could be convection, but radiative transfer, radiation. Hydrostatic equilibrium, here the atmosphere is being held up by pressure against gravity. We have the ideal gas law, and we have photochemical equilibrium. So you could imagine having an atmosphere like 1D atmosphere divided into layers, and your goal is to find out the temperature, pressure, and density, but with the ideal gas law, you can drop one of those. So temperature, pressure, the chemical composition at each layer, and the radiation at each layer, because ultimately you care about the radiation coming off the planet, because that's your spectrum that gives you that you can measure. So you could think of it like 5 equations and 5 unknowns, and you'd all know how to handle that, but it's one of those unfortunate problems that it's nonlinear. So you can have in scattering, you have intensity on the one side, the derivative intensity on one side, but then the intensity is on the other side, and things sort of depend on each other. You have nonlinearity in terms of like x squared or what have you, or double derivatives in some cases. So you cannot just like invert a matrix. We resort to something we call atmosphere retrieval. It's an inverse method. So I'm pretty sure many of you use inverse methods of some kind. That's like inverting the matrix, but it's more complicated. And we have a thing we call atmosphere retrieval. But atmosphere retrieval, I'm going to come back to that in a minute, but I wanted to just highlight some challenges. Exoplanets are far away, everything's spatially averaged, it's averaged in 3D, like a point source. And we do have a lot of lack of input. So we have in nonlinear physics, we have a lack of input values. And this leads to poorly defined boundary conditions. Like remember the water phase diagram, it had just so many lines through it? Because in many cases, we don't know the interior energy that's driving where the temperature at the bottom of that atmosphere is gonna start. Is there tidal heating? The planet was born with a lot of energy on the inside from gravitational potential energy, but it's slowly leaking out. And that exacerbates our problem. We also have some unknown photochemistry. I just picked one example to share with you, which is kind of, I'm like always astonished by this example. It has to do with our planet Venus, which you all learned like in elementary school is like 97% carbon dioxide. But in photochemistry, that carbon dioxide is broken up and it should go back as it recombines back. Let's think of CO2. What can you make out of that? Well, you can make O2, CO, and CO2. In the 1980s, when people worked out what it should be, they found it should be equal parts. In the atmosphere, photochemistry should split up CO2, and it goes back to equal parts, O2, CO, and CO2, but we don't see that. So it means one branch is preferred. And these folks decided there had to be a catalyst in the atmosphere, a molecule that itself remains unchanged, but we don't see it. And it forces that reaction to go back one way. Like how crazy is that? I mean, think about an exoplanet. And so in this case, they said there's some chlorine molecules. So on Earth, those would be dissolved in the water. And eventually people did find some chlorine molecules, like HCl, that not in enough quantity to close the story, but that are doing this job. So there's a lot of unknown chemistry there. And we also have other things like the way that gases diffuse up. We sweep that under the rug in a term called eddy diffusion, and we can vary that. So it's kind of complex. But we live with these unknowns by performing retrieval. We're retrieving the underlying physical parameters from the data. And the simplest way I can explain that is imagine just, actually I think I'm gonna explain that. I have this other one from Ryan McDonald. So, and I know that in your own field sometimes you might use this, but I just love this set of slides, so I wanted to explain what retrieval is, because it's gonna be key to finding signs of life beyond Earth for now. So we're gonna just throw models at our data and see which ones fit. So you're seeing a transit light curve, a transit spectrum on the left, it's just made up for this purpose. Amount of light blocked, you see the fake data by the points of error bars, and you see the model. Do you like this fit? Yeah, it's a cartoon, so yeah, it's good, all good. And in this instance, they're extracting temperature and water, so those are what we're looking for in our model. Good model. How about that fit? Bad fit, yeah. And so then they say bad fit, bad model. And you could imagine running like 1 million, 1 trillion models to see which fit. And eventually, you can end up with some confidence contours of how well it fits your data. And you can actually convert it into a probability, and at the end of the day, you end up with some hard numbers of what you found. Now we don't just run 1 million models, some of you do Monte Carlo, Markov chain Monte Carlo, you have other clever ways to step through the data, because you don't have time to like do it all. And this is how we find out what we're getting. And I'm not sure if the person was just kidding at 4 plus or minus 2, but we actually, many of our cases are like that. We can tell you I'm like extremely confident, maybe at the 99.9999% level there is water. But when it comes to telling you how much water, it's quite uncertain in many cases. So we have this retrieval, and a lot of you have seen like these types of corner plots before, and we try to figure out what's going on. And this isn't meant for you to laugh at, I just have an important point to make here, but now this Ryan McDonald, he is divided up into the forward model and the retrieval. So you have to make a model, because remember, your retrieval is going to step through parameter space and find all the models that fit the data. And one of the issues we have is that you can't have a really legit, sophisticated forward model, because it has to run like super fast. You're still running so many instances. And so you have to parameterize things and like ignore some of the physics and just kind of get a simple model. Question, yes?
Your models, are they vertically homogeneous, or do you allow for layering and clouds?
Good question, and there's some of each. Typically people are doing 2 kinds of models. One is like generated a giant grid. that can include the non-homogeneous and clouds, and you can work through the grid. Other times you want to do like free, so you're not constraining yourself to your thinking, but you're letting the code figure out what's there. And not too many people can yet do like non-homogeneous, not in all the molecules anyway, because it's just too many free parameters. So yeah, the bottom line is that maybe I won't dwell on this, but just to say there's a lot of details. And to understand what's going on, hopefully you've had time to glance through some things that sound familiar, like parameter estimation. Like there's a lot going on beneath the hood when you're going to hear about an exoplanet atmosphere. So I think I'll just leave it at that, and I'll tell you one of the successes we have right now, where we have this beautiful spectrum, transit depth as a function of wavelength. We have observations and data processing, and then we have our retrieval that gives us our model inference, our temperature, how much water. And this is just like a high-level overview, but it resulted in this, everyone loves to get a cover. This was a Nature cover called the popcorn planet. This is a planet that's very, very low density. And this planet, no matter what you did, always appeared to have a really high temperature at the bottom on the inside. And this planet has a slight eccentricity. So observation, data, inferences of like what your retrieval of your abundance is and your temp energy, and said, you know what, this has to be tidally heated because we can't explain why it's so puffy and why it has so much energy. So to me, this was a success story. We have some clear features, we got model, and we'd really like to keep doing this. So, okay, that concludes like just this little atmosphere part of the talk. And now with all that knowledge, or that kind of very, very overview-ish, we're going to return to these mini Neptunes now. But I did want to say one thing, is that we can't reach down to an Earth-Sun twin with transmission spectroscopy, because the atmosphere, that's like the skin of the onion on an onion, it's so tiny against the backdrop of our sun. This James Webb Space Telescope, we just can't get down there yet. We'd be doing, remember we talked about 3 parts per thousand? Our Earth would be like 1 part in a million or smaller, and we're not going to be able to get there. But we have 2 other types of planets. One is the sub-Neptune sized planets. And their atmosphere to star, okay, it's not 0.2%, but it's maybe like 0.01%. And I'll talk about those, and then I'm going to move on to the TRAPPIST planets, TRAPPIST-type planets, really small planets around even smaller stars. This is supposed to be all to scale, by the way. And I tried to estimate those numbers. If you find a mistake, just let me know, but it's probably okay. All right, so that's our future for the search for signs of life and our status. We just have the sub-Neptunes, which might be water worlds, remember? Or we have these small rocky worlds. Okay, that was the math for the undergrads, sorry about that. Okay, so these sub-Neptunes, we started working on this, before they were any. And my former student, Leslie Rogers, she's faculty at the University of Chicago, and we came up with kind of 3 N members of what could these sub-Neptune planets be. Because their density is ambiguous. They're kind of this very medium average density, and we can't tell what they're made of. So we just put up 3 N numbers for you. One is a true mini Neptune. So take our own Neptune and scale it down. This would like be a hydrogen-helium envelope, some water of some form. It's not going to be supercritical or vapor, but some kind of high-pressure ice, hot ice. We could have a case of our water world, 50% or more water by mass. Remember, it could have a supercritical water. It could have this gas layer dominated by water. And the third one was just like thinking of a giant rock, like a planet that formed like Earth but was more massive and outgassed hydrogen, so it has a hydrogen envelope. Like this is maybe neither here nor there for you, but the point being that this water world thing is something people really gravitated toward, maybe emotionally, because water means life and it should be all great. So where we're at now is people want to use atmospheres to sort through all of these. Because if you look at the picture of the atmosphere in this cartoon, they're all a bit different. And so that's where we're at. And I don't know if any of you have been following this, and that's why I'm really excited, because it's like so brand new. And so I'm going to try to work through where we are on that. It's a little more complicated than we expect. I guess that's what life is. It's never just the simple N members. But I'm going to work through it for you and tell you what I'm not working on this myself. Many of you know Bjorn Benneke. He's a professor at the Université de Montréal. He's one of my former students. And this is his data. So you've seen transmission spectra now. And it's the white points with error bars. And they've labeled for you what they're seeing. There's water vapor and methane, a bit of CO2. So 5 bands of methane robustly detected, no ammonia gas detected. One cool thing about no ammonia gas being detected is ammonia, as compared to methane, is extremely soluble in water. It's like orders of magnitude more soluble. So we astronomers thought initially, because you know how like I'm telling you some geo, like chemistry, we're trying to learn all that, but being an astronomer at heart. So I got really excited to find out that ammonia is extremely soluble in water, because if you have methane in your atmosphere and you have lots of hydrogen, so remember every atom wants to preferentially be in its hydrogenated form. You have H2O, you have CH4, trust me, you should have NH3, you really should. And it's just like a really weak signal, but it should be there. But if it's not there, wow, maybe this means there's a water ocean. So we got pretty excited about that, until the geotypes told us that, you know what, ammonia is extremely soluble in magma, and methane is not either. It's not ammonia itself, but it's nitrogen products. So unfortunately that is not a good telltale for what you have. So this team worked on this data, and they decided that the mean molecular weight of the atmosphere was too high. It can't be hydrogen, it has to have heavier stuff in it. And it has so much methane, it doesn't have ammonia, it has water. And they've settled on this far right one here, that there is this, wait, sorry, let me back up on that. Shoot, I think I might have made a mistake because I just put this together. Okay, all right. So let me just say they've gone through this whole thing, they've gone through the retrieval. They've ruled out these actually. They ruled out these, they ruled out all the scenarios I talked about, and they came up with a new scenario. And that's really exciting for us, but the mean molecular weight of the atmosphere was high enough that they said, and sorry, I made a mistake here because I thought it was going to be the one on the far right there, but they claim there's an atmosphere that is a mixture of methane, water, and hydrogen. So it's like all mixed together going down. So there's no water ocean here. But this water, hydrogen, methane atmosphere, it's like a very heavy greenhouse atmosphere. Hydrogen itself is very heavy greenhouse. It has no dipole moment, so itself doesn't absorb, but it gets collision-induced absorption. And that beneath that, it is a rocky world, like far below this envelope. But because of this greenhouse atmosphere and the higher pressures, it ends up being liquid. So they're saying that these sub-Neptune-sized planets, based on extrapolating from this mean molecular mass, that it's this giant mixture of this really envelope that's super greenhousey, and it's making not a rocky surface, but magma ocean. And that's also because of the lack of ammonia. So what do you think of that? That's like a totally different type of planet than was on our radar at all. It's something so new, we hadn't come across it. So that's unfortunate. I was actually at a conference this summer, and another student of mine, Madhu, he's a professor in University of Cambridge, UK, his postdoc, they actually unfortunately came up with a completely different interpretation. And I just want you to be aware of that because we're having some growing pains in the field. And now I'm showing you at the top, that's what I showed you before. Our expectation, we have observations, we have data processing, model inference, and we get a result that everyone can agree on, even if your code operated a bit differently or you had a slightly different data processing, that it ended up all working out okay. But where we're stuck right now is our reality is that our data, there are flares, there are spots, and even getting to our data points for our transmission spectroscopy is tricky because it depends on your model assumptions, and you may make a different assumption for limb darkening. And now because the data is kind of messy, it's a weaker signal, it's not as, the planet is smaller, the atmosphere is smaller, it's tricky. So now in our data processing, the things that didn't matter for a really strong signal, like red noise, the different modes are offset and we have to decide how to connect the different modes. These now end up really mattering in what our data even looks like to begin with. Now retrieval codes ended up being oversensitive to noise. If you were just going to do like chi-squared or statistical analysis, it wouldn't be overly sensitive to a couple of stray points, but for some reason we're still figuring out our retrieval methods are oversensitive. So you could have the same retrieval code, but a slightly different instance of the way the data was analyzed, and actually it might send you off into a different direction for some of the molecules. I hope you're with me on here, because you can forget about all this later, but I'm just trying to give you a snapshot in time of how this field is confronted with the amazing data from Webb. We're really struggling. And so you see here, we're trying to, Lewis Wellbanks and I tried to come up with this figure. We're still working on the best way to explain this, but now we could have different interpretations, even with the same data, because we may have a different retrieval code, or we may have analyzed the data slightly differently, and now we're getting a different answer. So somehow, one team had the same data set, And they ended up with a different archetype, the water world, with the hydrogen atmosphere and the water planet. And this other team ended up with they call it the vodka planet, which is a lot more memorable than what I said, because it's all mixing together. It's the water, hydrogen, methane, overlying the deep magma. So I hope you like that part of the talk, because the point was that for now, the sub-Neptunes appear to unsuitable with life. I think we'll find out what the consensus is as we get better data and time goes by and we fix our codes and figure out whether we have a super underlying mathematical problem with our models, or if we just didn't fully have it all together. But right now, they appear to be these really hot ones. And we need some colder planets to realize the water worlds if they exist. I just wanted to tell you one more thing. I hope I'm not giving you, I'm confident you can handle a huge flow of info. So I'm giving you a lot, but I have one cute little factoid that I was thinking about the other day, which is the TESS mission. So the MIT-led NASA mission is finding a lot of these sub-Neptunes. But this mission has a really unique orbit. It orbits Earth in a highly inclined, highly elliptical orbit, because Earth is bad for observing. We want to be far from Earth where it's dark. And you know, in an ellipse, it'll move slowly, and then it kind of zips by and then moves slowly. Well, we have a very special orbit with TESS because we're in resonance with the moon. So when TESS is orbiting, on the one time, the moon's on this side, and the next time around, the moon is on that side. The moon is stabilizing the orbit. It's so stable that the PI, George Ricker, he said the other day that if nothing like, if the detectors don't get wrecked or nothing goes wrong, it literally has enough fuel for 1,000 years or more because its orbit is so stable. Yeah. So TESS's orbit being in resonance with the moon, you might be able to guess what the period is. Because what's our lunar month, like 28 days? So the TESS orbit's like 13.7 days. And it looks at every field for a month before the sun gets in the way and you have to just kind of march across the sky. So if it's looking for about 28 days of each field, what kind of period planets can it find if it needs to see a couple of transits? Kind of 28 days, let's say, because you might see a transit at the beginning and then one at the end, or we look at the sky more than once. Well, TESS is not easily finding like cold enough planets because it's limited because of its orbit and its sky. It's kind of a weird thing that our moon messed up us finding cold enough sub-Neptunes. If you follow my argument, I'm just like, wow, I can't get my head around this. Okay, so those sub-Neptunes, at least for now, I never want to say never in exoplanets, because you never know what you're going to find, so I wouldn't want to stand up here and just say, okay, these are completely ruled out. But let's say for now, we're leaning towards this hot version, they're just too hot, there's no water, not going to do it. So we're now going to move on to these small worlds, and what is our status there? And some of you might have heard about the stellar activity ruining our efforts. Not everyone has heard, so I'm going to try to walk you through this. Here's a fake transit light curve. Transit depth as a function of wavelength. But right here, we're imagining an atmosphereless planet. So I want you to imagine a planet has no atmosphere at all, and we're still doing is the signal changing as a function of wavelength. In this picture, this is a little hard to grasp, but in this picture it is changing as a function of wavelength because there's a star spot. See the big polar spot? And it's showing you that, this is supposed to show you that the spot looks different at different wavelengths. But your way to think about that now is the numerator's not changing. Area of planet is the same the whole time because there's no atmosphere. But what about the area of the star? The area of the star is now changing because sometimes the spot is darker or brighter at different wavelengths. And so we literally, with a bare planet transit, can still have what looks like a planet atmosphere because it's not our numerator, but it's the denominator that's changing. And this actually is a really big problem. In our favorite planets, the TRAPPIST planets, Bjorn Benneke, the professor at University de Montreal, his student led a paper showing two separate transits of one of TRAPPIST 1b, which may not have an atmosphere, and it looks so different. Each transit is so different, the contamination caused by the spots is actually larger contribution than what you'd expect from the planet atmosphere. Yes?
What's the physical process that causes this wavelength-dependent spot?
What makes the spot?
Yeah, what makes the spot look different?
Well, the spots have their own spectrum. It's the same reason why the star has a spectrum, because radiation is going through and it gets absorbed by molecules, and this spot is cooler, and so it has like a different set of molecules or molecules in a different state. So your M dwarf star, for example, it will have water vapor in the star, and the spot also has water vapor, but but the water's in a different set of rotational vibrational states because it's colder. So the spot just literally has its own spectrum, and here's something. The spot is not a cooler star. People want to model it like, let's say, our star is 2800 Kelvin, and we're gonna assume our spot is 2600 Kelvin. We can't just put like a cooler star there. The spots end up having their own temperature structure because of the magnetic flux tube that's creating it. Yeah, so it has its own wavelength dependence because it really is just part of the star. It's just a slightly different structure. So it's kind of unfortunate. But there's a lot of work in this field. So let's imagine now we take our simulated star and we have our simulated planet. And yeah, so now we have this combination. So one of the biggest things in the field, right, I almost could just end my talk here because this is the status of the search for life. It's the James Webb Space Telescope, it's the planet atmospheres, it's this contamination. And so if you go to a conference on exoplanets or you're working at the forefront, you're trying to deal with this in 3 ways. One way is empirically. So we have some spot crossing events. People just want to make you're gonna hate I know this is being recorded, okay, so it's bad to criticize my own field, but you just, add something else to your retrieval code. Let's put in some spot spectra, whether they're generated from a computer or it is a cooler star, and some filling factor, and just kind of go from there. So there are those 2 approaches, and I'm part of the team who's generating actually cooler stars and their magnetic activity structures, so we can validate the models and get real things. But I have one really cool thing to tell you that's pretty exciting actually, and it's, I'm like a kind of peripheral part of this team, but it's an idea of how to handle this empirically. So the TRAPPIST-1 system has 7 planets, and remember, TRAPPIST-1b appears to not have an atmosphere. And because the planets are all pretty close to the star, so you can get near simultaneous transits. So there's a large observing program by Nestor Espinosa and his student Natalie at Johns Hopkins University to observe the planet without the atmosphere going by, and you get the one on the left. And then like immediately after, observe TRAPPIST-1e, our favorite habitable exoplanet candidate, exoplanet, our favorite exoplanet that's in the habitable zone, right after. So you get a snapshot of what your contamination looks like. So that's a clever idea, and got tons of time on the James Webb to try this out. Yeah, so stellar activity is where we're at, and I have a program I was going to tell you a bit about it. I might run out of time on this, so I'll just give you like an overview on some of the things that our team has been finding. I can't take responsibility for all of this. I'm just sharing with you like what happens when you care to more decimal places than you ever have before. Well, for limb darkening, the Kepler Space Telescope found out that, limb darkening isn't exactly what we thought it was. And again, it's to some decimal places that normally you wouldn't care about. But remember, the transit depth matters on how you fit that transit light curve. But it turns out the limbs, for some like stars, Kepler found this empirically, they're less dark. So there's still limb darkening, it's just not as strong of a gradient. And it ends up, if you make in your models surface magnetic fields, they end up making the limb less dark because it changes the way that the surface is heated. And there's some more detail I could go into if you want, but models from my colleague who's running these models team reconciled this by showing that if you have a star with this magnetic field, you actually get this lower limb darkening at the edges. And so the flip side of that is you could measure the magnetic field of the star if you can measure limb darkening precisely. On the bottom right, we just put out a little paper saying that if you could move to infrared, in theory, your contamination should go down. And I'll just show you, because I know it's like theory and stuff, so I felt compelled to give you some theory. So you all have seen the black body. This is just log flux. The units aren't important, it's just on a log scale, and wavelength in microns. And this, you could all generate this. This is just black body of different temperatures. So the intensity goes down overall, the peak shifts to the right. But what's important here is the Rayleigh-Jeans tail. I don't know how many of you remember this, because I know a lot of astrophysics is not radiation. But if it is, you remember the black body function, you do the little trick for e to the x, 1 to the x, and you see that the black body becomes linear in temperature. So it's no longer exponential in temperature, it's linear. And you can see it from the plot here, even though it's on a log scale. Do you see how it just flattens out here? So the flux difference for a difference in temperature is way bigger at shorter wavelengths, and as you go to the infrared, the flux difference for a difference in temperature is just smaller. And it's just a property of radiation. So we wanted to just kind of explore this idea, and we wrote a paper, and I may run out of time to tell you a bit about it, but just think of it like this. The spot's a different temperature, right? And so the flux difference is what ends up contributing to the contamination. But if that flux difference is less for the same temperature, it just becomes less contamination. Also, it has to do with the vertical, like your thermal emission features are created by a vertical temperature gradient. But if the flux changes less for the same vertical temperature gradient, then contamination also is less because the spectral features get squashed. So this is showing you signal in part per million and wavelength in microns. This curve is the star. It's just the features from the star with a spot of a certain kind. So it's doing something. But just to show you how they get compressed, we remove this Planckian function. We remove how it becomes more linear in temperature, and your features would be so much bigger. Let me say it a different way. The spectral features are getting compressed if you go to infrared wavelengths because of this property that the flux difference is less sensitive to the temperature gradient. And there's the horizontal temperature gradient due to the spot and normal star, and there's the vertical temperature gradient that creates the features in the first place. So if anyone here, I know almost no one's working on exoplanet atmospheres, but your transmission spectral features are always way bigger than your secondary eclipse emission features, because the emission features are getting squashed by this property. So we wrote this paper, pretty excited about theory, but the problem when confronted with observation is that as you move to the infrared, your detectors are noisier. And then it sort of wipes out the advantage that you've had, because even though your features are compressed, the error bars are just bigger in the data, so it doesn't necessarily help that much. Okay, so I covered most of the status of where we're at, that we wanted to look at the water world, but we don't think the planets we hope for water worlds are, because they're too hot, and at least the two we've been able to study in detail so far, they're this weird atmosphere with the magma underneath. We have the TRAPPIST planets and a few others, rocky worlds in the habitable zone, but the problem is that we have this stellar contamination and we can't get a clear picture of the atmosphere yet. So it's kind of a snapshot in time, and you need to have more speakers come back. If you have an atmosphere speaker once a year, you can stay on top of it. And hopefully in a few years, we'll have solved all these problems and won't have to talk about them. So to wrap up my talk, I didn't want to leave you without all the gases and tell you that we have 3 things we're thinking about when we're wanting to think of imagine we've solved all the problems, it's 5 years from now, what gases do we care about? We have 3 things we care about. I think it will make sense to you. We need a unique spectral feature. Unique compared to the background gas, like carbon dioxide or whatever gas you expect. Look, it's got to be produced in reasonable rates. We can't have a rate imagine how much methane or oxygen are produced on Earth. If you say, hey, I need 1 million times more, it might be the back of the envelope check is just maybe not work. So photochemistry ends up being so important because gases are created, but they end up being destroyed directly or indirectly by photochemistry. So it's like a back of the envelope check we have to do, but using our photochemistry codes. Finally, it has to not have a significant false positive. We humans were breathing out carbon dioxide, that could be a really good biosignature gas because we're all breathing it out, but it's already there, so it's not really helpful. So those are the 3 things we look for, and if you take a glance at this, do you see any biosignature gases that the community agrees on are good? Is there any row that's all green? One of these gases, it's called DMS, dimethyl sulfide. And yeah, I just saw a paper on it today. Another paper on it just literally came out today, talking about how this gas can be made by photochemistry in high enough quantities to mess us up. So we are working through gases, we are doing our models. At the same time, we're trying to sort out how to handle our framework when confronted with the amazing new James Webb Space Telescope data. So to summarize, we use these exoplanet mass radius models to infer the planet bulk composition. Atmospheres and interiors, we have limited data, so it motivates these suites of models and inverse methods. The atmospheres hopefully can help us identify water world, and one of the themes of my talk was it's a maturing field where we need a way to constrain all possibilities given the data. We do have some growing pains here. So we have to just basically stay tuned. We're confident we can solve all the problems in our methods, in stellar contamination, and hopefully a few years from now we'll have had some success in observing the atmospheres of rocky habitable zone exoplanets. And instead of saying current status, we can say something more definitively about identifying or not having found any biosignature gases. So thank you very much for your attention. And we have a few minutes for some questions.
Yes, we do.
Yes.
In that table you just showed, I think phosphine. Yeah, I was wondering why it's red, but it has a check mark in it.
I just put that because I love phosphine. So we have, I don't know if you have an emotional connection to your work and you're like, I just can't like say this is terrible. But okay, just the kidding. But one thing we do is oxygen is like really bad for, I mean oxygen is good for us, but it's kind of bad for photochemistry and oxygen and ozone and water vapor. And they make OH, which is the garbage eater of our atmosphere. It literally destroys everything. And so you have to have giant production rates to sustain stuff against OH, like, yeah. And so we try to model these in an anoxic atmosphere. So if there's atmosphere out there that are dominated by hydrogen, or maybe they just are carbon dioxide with no OH or less OH, it's better. So there's relatively reasonable rates for phosphine, but they're not great. So it was kind of an in-between case. Yes?
You've been talking chiefly about detecting any kind of life, but on this one you have a couple of techno-signatures. Could you comment at all about, is there something that would be a slam dunk for a techno-signature if we saw it?
Great question. That's what I was hoping. I was hoping that because most gases, like the way I try to look at it for gases is the environment has the same starting molecules to work with that life does. So this molecule, dimethyl sulfide, it's made by phytoplankton in quite large amounts. But hey, the atmosphere can make it too. So we're hoping that really complicated molecules like chlorofluorocarbons are our favorite, and people want to say, hey, those are only produced by life for sure. And one thing about our life on Earth is we basically almost never use fluorine, only in very rare cases. Fluorine's so electronegative, it's like the super glue of atoms. And why would life use something that's impossible to break up? Because they have to recycle. So people love chlorofluorocarbons, but you know what? For everything people are sure about, there's one small like cottage industry that can pop up and say, I can find a way that that's not true. And one way we think that some of these chlorofluorocarbons may not be true, it's a bit contrived for sure, but if a planet has no water, fluorine may take the role of hydrogen, capping off molecules, and then you could expect life to find a way. Yeah, it sounds a bit thin, but you know, can you be 100% sure? No, but will you be more sure? Yeah, maybe, like SF6, another favorite, sulfur hexafluoride. You wouldn't have heard of these unless you were working on technosignatures, but I've given this talk to physics audiences before, and someone in the audience will know that molecule. Because it's this inert gas used in industry, like to fill machines of some kinds, even in physics departments. So sulfur hexafluoride, life rarely uses fluorine. It never uses fully fluorinated molecules or non-carbon molecules. So I think we'd be excited, but it's so hard to make an airtight case. Yes?
I guess I'll ask about this slide too. Are there specific combinations of some of these molecules that would like always go together? Like, can you kind of learn more?
Yes, and that's a really good question. Can you have combinations that rule in or rule out? Yes. So if you're going to say that volcanoes is like pretty much the most generating false positives, you could say if my volcano is going to generate X molecule, it should also generate Y molecule, and then see if they are both there. People love, like from the 1960s, it was we should see for oxygen and methane, they should never exist together. But sometimes there's challenges, like our own Earth, we never had a lot of oxygen and methane together in our history, and people have argued that it's not realistic for our own planet, because we think we had a lot of methane in the old days, but we didn't have oxygen then. Now we have a lot of oxygen and almost no methane. There are other more complicated combinations, so it's definitely an active area. Yeah. Yes?
I was just curious, all the data you showed are from JWST, and there's now growing interest in using near-infrared ground-based high-resolution spectroscopy. And I was just wondering how that would fit into, say, breaking the degeneracy of star spots versus exoplanet atmospheres.
Yeah, great question. Yeah. I was very focused on what we have now, our James Webb Space Telescope, but the large ground-based telescopes. Obviously in North America we're hoping to get one, TNT, right? I mean, but the Europeans have EELT, and it is literally being built. You can look online and see like the structure of the dome, and the dome moves. And they're going to have an instrument called METIS. It's not METI, and METI, yeah, it's METIS. And they're actually going to be looking in the near infrared, and they have a chance to observe Proxima Centauri, one of our nearest star. And they're going to be looking in reflected light direct imaging, so there's no transit here. The instrument will block out this starlight so we can see the planet directly. And in that case, you don't have to worry because the star's gone. So next generation could be a lot better. That first instrument can't see like a ginormous number of these though. So it's still limited in number, but it will definitely, the future has many more opportunities for us. Yes?
So far as retrieval codes are concerned, you mentioned that models are different and that could lead to different planets being envisioned. What is the way to hone in on, because 3D GCMs would be kind of ideal if we could get everything together and then
well, it's not so much the 3D GCM that matters. It's, ultimately this retrieval is giving you like a probability, a posterior distribution. It's trying to give you like, and it's really in that. It's in how is it figuring out its confidence for what it's finding actually. I mean, there's several trains of thought here. I'm probably the only, I and one other mathematician I talked to, maybe the only ones that think there might be a fundamental problem. Like discretization that the instrument has and that our code has could be a problem. Because when people discretize in different ways, they can get a different answer depending on the data, so it's not clear. Other people think it's just a matter of figuring out what are all free parameters, how do the methods be more sensitive to one thing versus the other. So I don't know if there's a really solid answer yet. Different people are thinking about different things. There is one thing I forgot to mention though that I thought was really important. When my student and I introduced retrieval, at least I had intended it only to be used to quantify. So you see water, but how much water is there? Not to find a signal in noise, And so I think those are two different things, and we're mostly often running into trouble where there's a very weak signal. And then different codes will kind of try to do something different with that weak signal. Yeah. There's no really good answer yet as far as I'm concerned. Yeah. Ivan, yeah.
I'll ask a question naively. I'm imagining some kind of archetypal solar nebula forms a solar system with a bunch of planets. How sensitive would the atmospheric chemistry you get in those planets depend on the composition of that nebula, and would there ever be predictive value from the spectra of different stars,
Great
especially
question.
ones that
Yeah.
don't transit?
Well, right now, one of the things, so we might be able to sort through that for giant planets because they're supposedly maintain everything they were born with. But for these rocky worlds, really anything goes. It's just like our own Earth, we have a secondary or tertiary atmosphere, and so we can't really do that. I mean, ideally one day maybe we can. That's why I said that some people, like I said yesterday, it's like a wave function or like a quantum probability. Like we could do what you said, but we would inevitably have many things, there's so many unknowns, we'd still come up with many options. So far, we're far from being able to do that. And because planets have reprocessed, like that magma ocean, if it cools, some gases made it out like a game of musical chairs, others didn't. And how it all evolves, it's not clear if we'll be able to ever make the full prediction.
You said at the beginning that Earth-like planets are not good targets. Will they be with this habitable world observatory?
Yes.
And how many would there be?
Well, that's the phrase I like. Another phrase I really like is, there's this phrase, all roads lead to Rome. So I like to say, all roads lead to a kind of habitable world observatory, trying to find that Earth twin from space. You have to go above the blurring effects of Earth's atmosphere, block out the starlight so we can see the planet directly. And NASA's Habitable Worlds Observatory aims to do that. It won't come for decades, unfortunately, because there's not enough money now and it's very complicated. But how many it finds, that's a value proposition. It's for the community to decide how many is valuable. Like, you might say, look, I just want to hammer away at the 10 brightest nearest sun-like stars and see all the things that are there. I know there's going to be something. Or you might say, look, for that kind of money, we really need another Earth. In fact, we need 25 of them, which is what the committee said. And so then you have to kind of make a guess as to how common they are and how many stars they need. So how many stars can it look at? Hundreds of stars, but it would be designed to find 25 Earths.
So as a follow-up, I heard a talk by Joe Silk last week on the future of cosmology, but it included, intriguingly, this question of looking for life in the universe. And like he was pushing for cosmological experiments on the far side, he was also pushing for optical infrared telescopes there. And he was trying to make the case, I believe, for having telescopes situated there that can do these amazing things for exoplanets. Have you been following that at all?
Like I do follow it a bit, but one of the things is for, if you work in space, like you can go to space, you can send stuff there, it's hard. But the thought of like going to the moon, landing on the moon, dealing with the dust, it's definitely not easy. I think there's some use cases people love, like radio, because you need very large structures or lots of them. And it's a protected environment, and the dust isn't a problem there. So it just depends on which use case you're talking about, whether or not it's useful.
Thank you. Well, if there are no further questions,
I did have one to go.
okay, good.
What do you think would happen culturally, psychologically, spiritually to humanity if you discovered an unambiguous signal? Is that something you prepare for?
Well, I'll tell you what, I do see it more like the Copernicus revolution. So I just want to walk you through that, and that will be a good place to end. I know I really wish we'd have that unequivocal thing, but it may be more like, think of this Copernicus revolution. So Copernicus put out his idea that, hey, our Earth is not the center of the universe, our sun is. And that Earth goes around the sun and all the planets go around the sun. You know, some people bought into it, others didn't. But it actually ended up taking hundreds of years for this to be fully agreed upon by everyone. It ended up taking Newton to invent calculus. It took Halley and Halley's comet to return, that people fully believed everything without a doubt. Now, I could be wrong, I'm not a historian of science, but I think about that, and I think, did people's everyday life change when Copernicus put out his idea? I mean, some people got in trouble, like Galileo and others, so maybe it did affect them, but in general, not really. And it took so long to be accepted that it wasn't like a aha moment that everyone celebrated. It was kind of a more gradual thing. So it wouldn't be a bad thing, we just